Thanks everyone for attending today's webinar titled Slab-On-Grade Design Considerations. This webinar is presented by the Concrete Materials TRG and is the first in an anticipated three-part series on slabs on ground. And just to clarify, a discussion regarding the slab-on-grade versus slab-on-ground terminology is going to be offered later in today's presentation. The webinar series is intended to bring more attention to this practice area, as slabs on ground represent a significant portion of floor construction around the world. Virtually all residential, commercial, industrial, retail, and civic projects have at least some slab on ground component. And in addition to this webinar series, a slab on ground task group was recently formed as a way to document and share information regarding WJE's work and experience with slabs on ground, which can often span across several technical disciplines. As a result, this group will work closely within multiple TRGs, such as the Concrete Structures, Concrete Materials, and Coatings and Sealants, among others. I'm the group's coordinator, and I welcome you to visit the Slab on Ground Task Group's Still Under Construction portal site, which can be accessed through the Concrete Structures TRG. And contact any of the core group members who are listed on the site for more information or if you're interested in participating. Today's talk, Slab on Grade Design Considerations, will present information regarding typical design, detailing, and performance considerations regarding slabs on ground. It's presented by Todd Nelson and Koray Tureyen. Todd and Koray are both senior associates in the Janney Technical Center. Todd has been with WJE for 12 years and is a core group member of the Concrete Materials TRG, the Concrete Structures TRG, and the Slab on Ground Task Group. And Koray has been with WJE for 10 years and is a core group member of the Concrete Materials TRG and the Seismic Engineering TRG. Thank you again for joining us. Now I'll turn things over to Todd and Koray.
Good afternoon. This is Koray Tureyen, and welcome to our presentation. We will be, Todd and I will be presenting today's presentation, as Steve indicated, and here are our learning objectives. I will be leading the first half of this presentation and will mostly focus on slab on ground behavior and design tools. Todd Nelson will talk about joints, mixture proportions, and other details that are considered in design. You may have noticed that we use the term slab on grade in the title, but we will refer to it as slab on ground because what we're really talking about is a slab built directly on the ground, which may or may not be at a grade level, and ACI recently has been pushing for the slab on ground terminology instead of the slab on grade, but they are interchangeable in a sense. Here's a typical slab on ground cross section. This figure is from ACI 360. What we have here is basically a material supporting the concrete slab, which may or may not be reinforced as shown. There is the subbase typically between the ground and the slab itself. You may see base and a subbase layer with different compositions. These layers are generally non-cohesive, such as sand or gravel, and their thicknesses vary. And we have our typical load. Shown here is a moving load, but the load could also be static, as from, say, racks, or it could be from uniformly distributed. Now let's talk about a little bit of concrete itself as a material. It is a great material because you can mold it into any shape and thickness, pretty much any thickness, but it has its quirks. It's not dimensionally stable after you cast it, after it hardens. Initially, it shrinks due to surface tension of water in the capillary pores, and then later by loss of absorbed water on the surface of the capillary paste. It may also shrink due to carbonation, but this is very little compared to the other two. It not only shrinks, it also creeps, both in tension and compression. But let's forget about it for this discussion. This tendency to shrink due to moisture loss brings some challenges with it, to put it mildly. In fact, it does make a mockery of some of the ACI requirements on flatness of slabs. You could easily exceed those just due to shrinkage-related curling, as we'll talk about later. And if we were to cut a cross-section across the slab and looked at the relative humidity in the slab, we may expect to see a variable moisture distribution with depth. And I've got several, the vertical axis here shows the distance along the slab thickness, the horizontal axis, relative humidity. And I have drawn here the possible moisture distributions, relative humidity distributions with age of slab, at 3 days, 7 days, and so on up until 10 years. I've just drawn these things. You might expect to see it on a slab cast directly on ground or not protected for moisture from underneath. And at 10 years, you might have still pretty close to 100% relative humidity, but the top of the slab will have very little moisture. And this can be idealized with the blue straight line as shown. And the shrinkage associated with the loss of relative humidity, loss of moisture, will also follow the same similar profile. If we analyze the slab under a shrinkage gradient as shown, we will see that the slab will try to deflect into a bowl shape. This is due to the bending effect of the shrinkage gradient on the slab, and it is commonly referred to as curling or warping in the industry. Note that the contact is lost along the entire edge of the slab, with the corners lifting up more than the edges. I'm showing a cross-section below the three-dimensional figure, where it shows the middle of the slab wants to really sink into the ground, or this is a floating slab, but it wants to sink in relative to the level it started, and the edges lift up. This is because the reason because the corners curl up more is the amount of deflection is a function of the distance from the center of the slab. Again, I want to emphasize this is a floating slab. But as we know, and as we've seen in the beginning slide, that the slab is supported. It's not free-floating. It's supported by a soil support system, which is generally assumed to be elastic, like a continuous sense of springs, if you will. The soil has a spring constant of K, which is expressed in pounds per square inch per unit deformation, or PCI. When I first came across this, it was kind of confusing to me. And the way to think about it is if a soil had a 100 PCI stiffness, it would deflect 1 inch under a pressure load of 100 pounds per square inch. That's one way to think about it. It makes it a little clearer for me. K, or the modulus of subgrade reaction, depends on the subbase soil system and is measured by conducting a plate bearing test. What you basically do is you take a 30-inch diameter stiff plate and you load it, and you look at load deflection curve, and which is typically nonlinear as seen in this graph below the picture, but you come up with a linear approximation for it. Because it's expensive, it's not often done. And as you see here, you need to bring the hydraulic ram, you have to find a reaction. In this case, they brought a grader. They're loading it, and you need to measure the deflections, and how are you affecting the soil properties with that grader right next to it? Those are all issues. But anyway, there's a 12-inch plate bearing test. It's very expensive to do. The 12-inch bearing test does the same thing. It requires less loads, but still not very often done because of the expense and the effort involved in it. Typical numbers for K ranges from 50 for highly poor soils, compressible soils, to about 300 for really good compacted soils. But 200 to 300 is a reasonable number for design. K can be correlated, has been correlated to what's called the California bearing ratio and resilient modulus. These are tests mostly used in the roadway construction work. And these formulas come directly out of ACI 360, and we can also relate it to uniform soil classification system. The California bearing ratio is the older test. The resilient modulus is the newer semi-empirical mechanical test and is considered more realistic. But simple relationships like I've shown in the previous slide may sometimes give unrealistically high K values. Therefore, it's always good to double check against your soil classification chart like shown here. And this is again from ACI 360 document on Slabs-On-Grade. And if you were to get like a, say a California bearing ratio of 4, that corresponds to a modulus of rupture of 125. And you might want to double correlate if you're like a soil type ML, which doesn't necessarily get there. Maybe there is something going on with moisture or with your classification, so you might want to double check. The subgrade modulus is influential in determining the thickness of the slab. The magnitude of K also should invoke a decision on the designer's part, and the engineer must decide whether to compact or stabilize the soil. And one way to do this is by adding a subbase layer. And the subbase layer has a certain effect on the stiffness that you get, but this chart illustrates you can get a fairly high relative improvement on a poor soil subgrade. For example, on this one, the curve goes from 65 KSI PCI for a 4-inch sub-base improvement to, you can increase it up to 110, 120 PCI with a 12-inch sub-base, but the gains are incremental, and it's typically you can't make a poor subgrade into a great subgrade by just adding a sub-base to it. That's what I'm trying to illustrate here. And the moisture content affects the K value that you get for cohesive soils. It may reduce or it may increase it based on the moisture content. Having talked about how soil support system stiffness is determined, let's look at the effect of support stiffness on shrinkage-related curling now. If we cut a cross-section as shown and looked at the deflections of our slab, and I've done basically modeling on a 15-foot by 15-foot by 6-inch slab, 4 KSI concrete. The deflection profiles would look like this for 2 different soil support stiffnesses. I've taken the 50 PCI range spring. I've supported the slab in the middle with 50 PCI springs, the slab at the bottom for 300 PCI springs, and I threw in the floating slab in there for comparison. The relative mid to edge slab deflection is reduced with stiffer support as seen here. In fact, the central zone of the slab supported on stiffer support, soil support, has less contact pressure than in the softer soil supported slab. And this has some consequences on the stresses that you get on the slab itself. Let's look at the effect of this on tensile stresses on top of the slab. These plots show tensile stresses on top of our example slab, supported by softer soil support on the left and the stiffer soil support on the right. These stresses are only due to, I want to emphasize this, there is no external load. These stresses are only due to shrinkage gradients of about 265 microstrain and the self-weight of the slab. Don't ask me how I came up with this 265 microstrain, but you know, it's not completely unreasonable. You can potentially get as much. But what I'm trying to illustrate is, as the soil support system stiffens, the stresses induced on the slab increases for a given amount of shrinkage. Note that for this hypothetical slab, the stresses induced on the stiff soil supported slab are larger than the modulus of rupture of the concrete, which is about 475 psi. And we're getting stresses as high as 650 psi. And there is potential to crack this slab just due to shrinkage and the slab's own weight. If we were to reduce the slab size to 9.5 square feet for the slab supported on 300 PCI supports, elastic springs, same slab thickness and shrinkage gradient would require, therefore, the stresses come down to about the same level as the 50 PCI supports. And so for the same shrinkage gradient and concrete strength, then we might want to use closer joint spacings for our slab supported on 300 PCI elastic springs or stiffer soil. And you can do several things, other things than just decreasing your joint spacing. You can use shrinkage compensating concrete construction. You can reduce the amount of shrinkage in your concrete by mixture. Todd will talk about that. You can use post-tension concrete to pre-compress it so it won't crack. Or you can use reinforced concrete, obviously. That's always an option to minimize the crack width and its consequences on the operations of the building or structure. There are other issues involved with concrete shrinkage and soil supports. The rougher the subbase surface, the greater the friction and the restraint to the slab movement, which are the ones that add to the cracking potential of the concrete. That restraint have an effect on curling, and it does have an effect on reinforcement, the amount of reinforcement that you want to put in. The most important thing for slab on grades, in my view, is the uniformity of the soil support system. Initially, you want to have a good geotech testing agency and QA/QC procedures to keep everything uniform. And in service, you would like to have a good design so you keep the moisture out from underneath the slab by deflecting it away at the building edges and putting drainages and so on. Having talked about soil supports, now let's talk about loads a little bit. The loads can be external and internal. The external loads can be concentrated loads, which could be static or dynamic in nature, like due to vehicular traffic. I called it static because pretty much nothing is static. You always get some sort of variation in the load. And it could be uniformly distributed loads, such as, if you had an above ground water tank or wastewater treatment tank, you could have uniformly distributed loads. Or it could be unusual loads due to construction, random loading, soil swelling, loss of supports. All these things are possible. The internal category, I called it, there are the environmental effects, which could be temperature and the moisture variation. And shrinkage of concrete material and carbonation of concrete material could cause internal loading. I called it internal loading, but it causes stresses, as we've seen earlier on the slab itself. This is a load type summary chart that I've clipped from a PCA slabs on ground document and correlates the type of external load with the type of stress that controls the slab design. In the upper part of this chart, the load types are listed, and the bottom part of this chart, bottom square, shows the controlling design consideration. As you can see, concentrated loads can have a wide range of controlling design considerations. It can be governed by concrete bearing, punch and shear, or flexural stresses. Under the distributed loads category, typically you would have negative moment in unloaded area might govern joint faulting, and if your loads are really high and the area is large and your soil is not good, then you'll have settlement issues with that. We can conveniently subdivide slabs into different types, and ACI, these bullet points follow the ACI 360 categorizations. The slabs can be unreinforced concrete slabs, the plain slab, for example, sidewalks, most light-duty warehouses like your typical Targets and Walmarts and so on, are built out of unreinforced concrete slabs. It has certain capabilities, but the most important thing is jointing in this type of slab. You can have slabs reinforced for crack width control. Most of your industrial pavements, industrial slabs on ground will have minimal amount of reinforcement to control the crack widths. And then slabs, you can reinforce the slabs to prevent cracking. And under this category, I've included post-tension slabs on ground and shrinkage compensating concrete slabs. You might not want your concrete to, you may not, for example, want to have a joint in your warehouse for wear resistance for later problems that might develop at the joints. So you could use these options. And structural, you can have a structural slab. The structural slab will have a good amount of reinforcement to be able to span over any areas of loss of support or any, in swelling soil areas, you might use these things. And technically, like in your basements, if you have a post supported directly on the slab, it should be considered as a structural slab, but most often it won't be designed as one. They'll just put in welded wire reinforcement and design the slab that way, 3-4 inches of slab. I just want to briefly talk about design methods, and the lower three design references are typically for pavement design. It's used for highway pavements or parking lot pavements. The references in the upper, other than the lower three references, are typically for industrial slabs on grounds. And all of these references or these organizations have developed charts of their own and their design methodologies, which you can find at these references. ACI 360 discusses several of these and compiles several of these and discusses it. It's a very good resource. The history of slab-on-ground design started in the concrete paving industry. Westergaard basically developed this from early 1920s through his passing in the 1950s. And he assumed elastically supported rigid pavement and real loads on that pavement to come up and solve a bunch of differential equations to come up with his equations for slab design, which has stood through the test of time, but it has been found, it assumes full contact between the slab and the soil, and it has been found if you lost contact due to, for example, curling, then it might be not as good a method. Burmeister had developed in the 1940s a layered solid theory, but it was not developed enough to be of use in design. And finite element methods since the 1980s has been used extensively, but mostly this is used for investigative work, the type of work that we might do. And most of the design work out there, design of slabs, are done by design charts. And there are dedicated computer software that basically runs the calculations using these design charts, but they are generally black boxes. And you have to be careful in using them. Here is a chart just for illustration purposes. I will not delve into too much of this. I don't want you to read everything on these charts, and I don't expect you to, but here's a chart developed by PCA for industrial trucks with axles equipped with single wheels. The chart has variables of wheel spacing, wheel contact area, and soil stiffness, K. From the chart, a thickness can be selected based on the selection of the allowable stresses. So you go in with an allowable stress here, and then you go find your effective contact area, and then you go down to your real spacing, and you go towards the right to hit the subgrade stiffness that you might have at your site. If you were to have, for example, 200 PCI, then this would give you about a 200 PCI soil support stiffness. Then this would give you 7 3/4 inches according to this chart. And if you had 50 PCI, it would give you about 8 1/4 or almost 8 1/2 inches. So it does make a difference in the soil slab thickness. And this contact area is a little tricky because you go find it from this chart, and it's not necessarily, the contact area is not equal to the actual area of contact. It's slightly higher than your actual area if you look at these curves in the PCA chart. Trying to. There are other charts for like traffic loading on unreinforced slabs. I took this from ACI 330. And in this case, what you do is you get in from the pavement thickness side. You can select the pavement thickness as a start. You find the axle load from these radiating lines. You go up and find your soil stiffness. Let's say it was 50 PCI. And then once you hit that curve, you go towards the left, and you find the flexural stress in pounds per square inch. And then you can divide that by the modulus of rupture adjusted by the factor of safety, which is where all the factor of safety comes in here, not on the load side. You typically lump it into the strength side. You come up with a stress ratio, which then you can come down to this other chart, which shows you the number of repetitions versus stress ratio. And let's say if we had a stress ratio of 0.5, and we had all of these curves represent a different reliability level. For more important jobs, then you might want to use a reliability of 95% as opposed to 50%. So if you were at a stress ratio of 0.5, then we have over 150 or 500,000 repetitions we can take for that particular axle type with a given pavement thickness of 6 inches, and so on. So anyway, without getting into too much detail, I just wanted to illustrate that these charts are available. For post loads, this chart is from PCA again, and similar to the other ones, you just need to know a couple of variables. Knowing the rack loads, leg spacing in each direction, and effective contact area for each leg, and your soil stiffness as slab thickness may be determined. And other design charts can be developed for a grid of racks at different spacings for aisles, whatever. If you were to have a loading, for example, in this case, I'm showing a line strip load example. In this case, negative bending moment in the aisle might be an issue. These steel bars are supported out of these racks, and you basically have a line load going into your slab here. And the slab will deflect as shown at the bottom here. And in these areas, you'll have negative moments. And flexural stresses, these areas represent the aisles. Flexural stresses may develop. And so you should not assume that you should put joints in the aisles immediately. So flexural stress-related cracking in the aisles might be an issue. If you have unusual loads, then you might want to use a computer program or a finite element method to analyze that type of slab. This concludes my portion of the presentation, and I will now pass it on to Todd.
Thank you, Koray. And again, my name is Todd Nelson. I will be finishing up the presentation and talking about some other design considerations for slabs on ground. There's quite a few other considerations that need to be thought about when we design slabs. And a lot of these considerations follow through in our troubleshooting of problems on slabs on ground and also the repairs. So hopefully you guys will be able to take some things from this presentation and use them in your troubleshooting projects. But I'm going to try to get through a discussion on joints, vapor retarders, concrete mixture proportions, and possibly some other details if we have time. Typically, in slab-on-ground construction, we have 3 different types of joints: construction joints, control joints, and isolation joints. And I'll talk a little bit about each of these moving forward. Here is an overview of a slab-on-ground. You can see we've got all 3 joints represented in this chart. We have isolation joints along the wall. We have isolation joints around each of the columns. We also have control joints running along the column lines, and the edges of the slab are considered construction joints. And this particular photo shows that this construction joint is actually a keyed joint, and the other side's a dowel joint. But that's just a basic overview of what you commonly see on slab-on-ground construction. Isolation joints. The goal of isolation joints is pretty straightforward. We're trying to separate columns, walls, footings, other fixed objects from the slab-on-ground itself. We don't want any vertical or horizontal movement. We don't want a connection across that joint. Sometimes we'll see the isolation joints called expansion joints. I commonly, in slab-on-ground construction, call them isolation joints. We typically don't see much expansion in slab-on-ground construction, with exception of few special cases. Here is a good detail for isolating concrete columns, or steel columns for that matter. The diagram on the left shows control joints coming into the column, and then we have isolation joints around the slab edges, and then we also have isolation joint around the column. And you can see on the photo on the right, and I apologize, it's a little blurry, but you can see the material that we align the interior slab to isolate the slab from the column is not only on that slab, but we also put it around the column itself. This material is typically a compressible material. A lot of times they use asphalt impregnated materials. But this detail is good because we're not only isolating the concrete slab, but we're also isolating the column. And the concrete gets placed in between the column and slab at a later date. Here's a basic isolation joint that we'll commonly see. Again, we have the compressible material between the slab and whatever member we're trying to isolate, and then we typically fill that joint with some joint sealer, just to keep debris and water and whatever else out of that joint. Control joints. In the WJE world, we see the most problems with spacing of control joints. And future webinars, we'll talk about some of the problems associated with excess joint spacing, such as increased curling, joint instability, random cracking, and so forth. But that'll be saved for future webinars. But spacing of these control joints is very important. A general rule of thumb, and you'll see these general rules tossed around in ACI 302 and 360. But the joint spacing should be, in feet, 2 to 3 times the slab thickness in inches. So if we have a slab that is 5 inches thick, the joint spacing should be 10 to 15 feet. With thicker slabs, and this is my experience and my opinion, we should probably keep that joint spacing at 15 feet. And this is based on my experience, and without any optimization of the design, I think we need to keep to that. The most common control joint that we see is a saw cut joint. We'd like to see this joint cut to at least 1/4 of an inch of the thickness of the slab. The joint should be cut as soon as possible after the concrete has hardened. We'll see joints cut these days by the soft cut method, and they'll be cut within 6 to 12 hours after the concrete is cast. With traditional hard cut methods, sometimes they'll wait 18 to 24 hours and cut them the next day. At these joints, load is typically transferred by aggregate interlock. In some cases, especially in unreinforced concrete slabs, they may put dowel baskets at the locations of the control joints to help with the load transfer. Here's a typical saw cut joint. This is pretty basic, but I just wanted to emphasize the depth of the cut, and that depth we want at least 1/4 inch of the total thickness of the slab. That this induces or should induce a crack right below that saw cut. At a later date, that saw cut will be cleaned and then filled with either a joint filler or a joint sealer. Construction joints, they're basically joints that are created from the end of one placement and the beginning of the next placement. The goal typically at these joints is to create load transfer across the joint, and there's various ways to do this. The most common ways that I see are square dowels or rounded dowels, and there's other methods as well: diamond plates, flat plates. There's quite a few others as well, and I'll talk a little bit about each one of those as we go. This is a very basic diagram of a typical construction joint. You see a smooth dowel bar that is cast into one concrete slab, and then the remainder of the smooth dowel bar is actually coated to prevent bond into the adjacent slab. This allows for in-plane movement in the concrete slab due to shrinkage or due to temperature effects, but we also get the load transfer across the joint by the dowel. Square dowels are commonly used. In square dowels, you'll actually see a metal or plastic clip that goes around this square dowel, and that allows for in-plane movement of the slabs. We also want to prevent the bond between the slabs as well. Here's a picture of a typical diamond plate dowel. I apologize, the picture quality on the right is not the greatest, but again, these dowels are cast into one slab, and half of the diamond plate sticks out and gets inserted into a similar pocket on the adjacent slab, again allowing for load transfer and allowing for in-plane movement of the slab. You can actually see a control joint here too that was cut previously, and as anticipated, we have the crack induced below it. Key joints, I haven't seen a lot of key joints. Recently, I used to run into key joints used for construction joints in the past. I typically do not recommend using key joints as construction joints. The problem with these joints is once you have volumetric movement of the slab, specifically shrinkage movement, both these slabs want to move away from each other, and that opens up the gap in between the key. And when that occurs, you're essentially losing any ability for that joint to transfer load. Vapor retarders, there's been a lot of discussion and a lot of different opinions about where we should place vapor retarders. I'm going to go through some of the pluses and minuses of the placement of the vapor retarder. In terms of terminology, I call these vapor retarders. Traditionally, sometimes they were called vapor barriers. I shy away from that term because barrier implies that no moisture is moving through that plastic sheeting, which is not true. Any vapor retarder that we use has some amount of moisture moving through. But the two scenarios that we commonly contemplate is are placing the vapor retarder right below the slab, or placing the vapor retarder below 6 inches of soil. First and foremost, I typically do not recommend that vapor retarders are used when there are no moisture-sensitive flooring materials that are going to be applied to the slab. If we don't have moisture-sensitive materials, I do not recommend using vapor retarders. The pluses and minuses of using the vapor retarder right below the slab are as follows. One, we get one negative is we get a moisture gradient between the top and the bottom of the slab. This is created because of the top of the slab wants to dry out more and dry out quicker than the bottom of the slab. The vapor barrier or the vapor retarder under the slab prevents any moisture movement from the bottom of the slab, but the top of the slab is allowed to dry out. So we get a moisture gradient there that actually increases the amount of curling of the slab. We also get a reduction of friction between the soil and the concrete. This will also lead to an increase in curling and shrinkage. And we also get excessive and prolonged bleeding, which can be an issue with finishing of the slab. Some of the considerations for putting the vapor retarder 6 inches below the slab, we need to consider what that soil layer is going to be exposed to during construction. If that soil gets rained on prior to placement of the concrete slab, it'll fill up with water. This water will essentially be an infinite water source for water vapor or liquid water to move through that slab in the future, which makes it very difficult to put any moisture-sensitive flooring materials on in the future. One benefit is if you do it correctly and you don't allow that soil to be exposed to rain or other water sources, you will get two-sided drying, which has its benefits from a moisture perspective. And it also prevents damage to the vapor retarder. If we put the vapor retarder 6 inches below the slab, we don't have damage to that vapor retarder because of construction activities on the top. And in terms of vapor retarder properties, I typically recommend at least 20 mils in thickness with a minimum of 6-inch overlap at the joints and a minimum perm rating of 0.3. Concrete mix considerations. I'm going to briefly go through some of the considerations in designing slabs on ground. Try to cover minimum strength criteria, shrinkage potential, the use of entrained air and fibers. Strength considerations, typically the minimum values that are required for the class and type of floor are easily met. We typically don't have too many issues of not meeting those minimum values. It should be noted that most of the design theories require a flexural strength or a modulus of rupture, so it's important to know what that value is going to be. We definitely don't want our compressive strength to be too high. If we have our compressive strength get too high, this will also increase our modulus of elasticity, making our concrete more brittle, which can lead to additional cracking or additional random cracking. Some special considerations where strength is more important include impact resistance and abrasion resistance. So these have to be considered in more detail when we have slabs with those concerns. The most important part in designing concrete mixture proportions for slab-on-ground construction is the shrinkage potential of the mix. We want to lower that shrinkage potential as much as possible. And one way of doing that is by lowering the cement paste content of the mix. And the most important factor in lowering that shrinkage potential is the type and quantity of coarse aggregate. There are some coarse aggregates that are particularly prone to volume change and shrinkage, and they should be avoided when possible on slab-on-grade, slab-on-ground construction. One of the concepts that we use to lower the total paste content is using a well-graded aggregate. Using a well-graded aggregate makes the concrete consolidate easily. Therefore, we have to use less paste in the system to make the concrete consolidate well. We also try to tend to use the largest nominal aggregate size possible. When we do this, the surface area of our aggregates goes down. Therefore, we don't have as much surface area to coat with cement paste, which results in using much less paste in the concrete mixture proportions. We also want to use a moderate water to cement ratio. I typically recommend a water cement ratio between 0.47 and 0.5 for interior applications. Depending on the use of the slab and the exposure of the slab, I may change these values, but typically for interior concrete, I recommend between 0.47 and 0.5. And again, we don't want our water cement ratio to be too high. When we get higher, our water content increases, which will increase our shrinkage potential. And if we get too low, our strength of concrete will go up. And again, as I talked about before, our modulus of elasticity will go up as well. And we want to avoid those in slab-on-ground construction. Other ways we can try to lower our shrinkage potential, we can use certain cements. I'm not going to talk about this in detail, but there's certain cements we can use that will lower the amount of shrinkage of our concrete mix. And we can also use shrinkage reducing admixtures. They're fairly new to the market. They've probably been around 15 years or so. I see shrinkage reducing admixtures used a lot more in the last 5 years. And these actually do work. I can only speak from experience. I've used Grace's line of products in some of my projects, and their products actually can reduce the ultimate shrinkage by as much as 35%. I've seen quite a few specifications for target slab-on-ground construction recently, and I've been approached by quite a few ready-mix producers that have this specification, this target specification they have to meet. And in this specification, they're required to have a 28-day drying shrinkage value of 300 microstrain. And this value is very difficult to meet with conventional concrete mix designs. In each project, these ready-mix producers had to use shrinkage-reducing admixtures. And by doing that, they were able to achieve that 300 microstrain requirement. Here's a table that shows the potential influence on various factors on the shrinkage potential of concrete. If we increase the slump from 3 to 6 inches, we can see a potential increase of 10%. And as I was talking about before, changing our maximum size aggregate will benefit. If we go from 3/4 inch maximum size aggregate, instead of using 1.5 inch maximum size aggregate, we can see a potential increase of 25%. Some other factors, cement, as I was talking about before, cement can affect our shrinkage potential in some cases by as much as 25%. Admixtures, any admixtures you use in concrete will affect the shrinkage potential. And admixtures that we commonly use in concrete have to meet the requirements of C494 to be approved to be used in concrete. And believe it or not, C94 allows an increase in shrinkage by as much as 35% and still be acceptable. So we can have admixtures in there that are contributing significantly to the amount of shrinkage that we have. In addition, high fines content in the coarse and fine aggregates can contribute by as much as 25%. And as I was talking about earlier, we can have high shrinkage aggregates. And that can increase our shrinkage potential by as much as 50%. So you can see a lot of these factors can add up quickly and significantly affect the shrinkage potential of our mix. Other considerations for concrete mixture proportions, one is air entrainment. We typically don't want to use air entrainment when we have a steel trowel surface. This leads to surface delaminations, and that can lead to surface texture problems. We also want to consider the finishability and placement of the mix. We don't want something that the contractor is going to have difficulty finishing, and we also don't want placement issues. We want to make the mix make the mix so it consolidates easily. And in ACI 302, they actually have an algorithm that you can follow to help you determine concrete mixture proportions based on a few of these design considerations that I've already went through. This chart shows the effect of shrinkage reducing admixtures on the drying shrinkage of concrete, as I was previously talking about. On our x-axis, we have drying time in terms of days, and on our y-axis, we have the shrinkage measured in microstrain, basically change in length per unit length. And if you look at 180 days, we have an approximate shrinkage of 420 microstrain with the use of the shrinkage reducing admixture. Compared to the control, we have about 550 microstrain. That's about a 25% difference in drying shrinkage. And I'm going to quickly go through some of these other factors as we're running out of time. Steel fibers, I typically don't recommend steel fibers or hybrid fibers in use in slab-on-grade for load transfer. I don't feel it's an effective way to get load transfer at joints. it may help keep cracks tighter, may help prevent some plastic shrinkage cracking as well. Other durability concerns that may be considered: abrasion, chemical resistance, and freeze-thaw. Each one of those has a specific consideration in terms of your mixture proportions. Some other design details, and I'm going to go through these quickly. I commonly see these two design details, and I definitely do not recommend either of them. They have thickened edges. The diagram on the left is a thickened edge at a column location, and I commonly see cracks that occur right at the end of this transition of the thickened edge. That's because of this concrete on each side of the column wants to shrink away from the column, and it's not only restrained by this thickened edge, but it's also restrained by the anchorage to the column, which creates a crack, commonly right at this location. And on the right, this is a typical slab-on-grade, slab-on-ground detail I see for residential construction. Same thing. I'll see a crack form right at the edge of that thickened edge. So we want to avoid these details. I think we're running out of time, so I'm going to skip over these and go to our summary. Koray did a great job of covering the behavior of concrete slabs on ground, and we want to be aware of how concrete behaves dimensionally, not only for design considerations, but for our troubleshooting projects and our repairs as well. Soil support is oftentimes the most variable and troublesome element in a slab-on-grade system. It determines our joint spacing and the thickness of our design, so we have to consider that. Use and loading will often dictate the soil support system and the type and thickness of slab to be used in a particular project. Koray did go through some design tools. These design tools are available through PCA and in ACI 360 as well. And we should keep it in the back of our mind that we have other tools available to us as well, finite element modeling and other computer programs. And there's quite a few other considerations we need to think about when we're troubleshooting slabs on ground. Those include joints, vapor retarders, concrete mixture proportions, and design details. And we'd like to thank you for attending today's webinar.